All right, so now we'll try to understand what exactly is the k-means clustering algorithm. So let us see the diagram and try to understand it step by step, what exactly is going on. So first we look at the top part of the picture, and the top part of the picture we have again the typical unlabeled data that we have been uh, discussing so far, because we don't have labeled data for unsupervised learning or clustering. So we have completely unlabeled data. And you can think of each of these dots as customers, right? So every dot is, let's say, one customer. So each and every dot is, let's say, one customer. So one dot corresponds to one customer. So that's the information that you have. And all that we are trying to do is we are trying to find what are the different groups and clusters of data. So it's a two-part problem that we are trying to solve. So we are doing two things. One, we are trying to figure out how many groups and clusters of data you have. That's A. And B, you are trying to find out what are the centroids of the clusters B. Okay, so there are two things we are trying to do. There are two things we are trying to do, and there are two problems that we are trying to solve. So first, we are trying to find how many groups and clusters of data we have. That's A. Okay, so how many different groups and clusters of data we have? So we can very clearly see that there are three different groups and clusters of data. And B, we are trying to find out the centroids of the cluster. So that is exactly what the algorithm will help us achieve. So what are the steps of k-means? So k-means I'm trying to take you through because k-means is a very easy algorithm, although the focus here is not too much on theory and algorithms, but this algorithm I'm taking you through because it's very simple. This is hardly 5 minutes it will take. So first, what we do is we randomly initialize k cluster centroids. So step one of k means what we do is we try to randomly initialize the k cluster centroids. Okay, because remember, we are trying to ultimately find out the positions of the centroids. We are ultimately trying to find out what the centroids are. So the very first step that we do is we try to find out what those k cluster centroids are. Okay, so k is a variable. So in this case, the value of k will be equal to 3. Okay, because I told you initially we do not know what the centroids are. So first you define k cluster centroids. You initialize k cluster centroids to start with. Next, what we do is we assign every single point to its nearest cluster centroid. You assign every single data point to its nearest centroid. That is the next thing that you do. And then you reposition the cluster centroids. Okay, then we reposition the cluster centroids. And we keep repeating steps 2 and 3 until no further assignment happens. Okay, so this is the algorithm of k-means. I know it's a lot to take in. So what I'll do is I'll try to give some animations and help understand this concept better. But just give it a glance again, all of you. So first step, randomly initialize k cluster centroids. Initially, you initialize the centroids here, here, wherever. You randomly initialize the k centroids. Step two, we assign every data point to its nearest centroid. So we assign every single data point to its nearest centroid. And step three, we reposition the cluster centroids. And we keep doing this over many, many iterations. Many iterations, we keep repeating the steps until no further assignment happens or the cluster centers stop moving. So that is effectively what we are trying to do. So just to help you relate to this a little better, I will parallelly open up this visualization for you. Let me quickly try to take you through this, pictorial approach. So I will take a simple example of a Gaussian mixture. I think it's very obvious here how many centroids and how many clusters are there, but let me anyways take you through it. So there are three clusters that are visible, and I want to find out the exact position of the centroids. So how do we do it? So first step is again, we randomly initialize three cluster centroids. So let's say I start with three random centroids, somewhere here, somewhere, and I'll try to keep it like a little confusing, keep it midway, somewhere here, and I will try to keep the next centroid somewhere here. So you can see the initial centroids are completely random. They are not perfect. Centroids are basically averages. Okay, so what is a centroid? Centroid is an average. Centroid is the middle value. So ideally, the centroids are supposed to be here, 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 and here. But as I said, this is not something that you will do manually. You will not do clustering manually. You want an algorithm to find out the groups and clusters for you. Okay, so you do the initial centroid placement, and then the algorithm will iterate and find out the exact position. So, okay, so first step is this. Second step, what we will do is we will try to find out the we'll try to find out uh, the distance of the data points from the respective centroids. So we will assign every data point to its nearest centroid. So if you look at all these data points will be assigned to red. The moment I hit go, if I click go, what will happen? All these will be assigned to red. All these will be assigned to blue. These are also blue because they are closest to blue. And all this will be assigned to green. So we are in step number 2 right now. Then we will do step number 3. We will reposition the cluster centroids. So reposition means what? Reposition means we will recalculate the centroids. So centroid is average. So initially the centroids were here, right? Green centroid was here. Now all these points are part of the green centroid, right? All this is green. So you will recalculate your green centroid, and the green centroid will move somewhere here. Okay, so when you update your centroid, the green will be here, the blue will be kind of somewhere here, and the red will be kind of somewhere in midway. So when I update the centroid, see what happens. The green moves here, the blue moves here, and the red moves here. We have completed step 3. Now we are back to step 2 again. The position of my centroids have changed. Now the green centroid is here, the red is here, the blue is here. Now with respect to that, you try to again assign every data point to its nearest centroid. Now with respect to this new centroid placement, which we just now updated in the previous step, now you try to again see, okay, which points are closest to green, which points are closest to blue, and which points are closest to red. So reassign points. Look at the magic. So now all these are part of green, all these are part of blue, all these are part of red. Now click on update centroids. That's it. So step 3 completed. Again, if I do step 2, nothing will change. So now you keep doing step 2, step 3, step 2, step 3. Nothing will change. Okay, so this is how the k-means algorithm works out. So we can do one more example, slightly more difficult one. Let's take a packed circle. So I'll define my 7 centroids: 1, 2, 3, 4, 5, 6, 7. Okay, so we initialize with the 7 centroids. So first step, you assign every single data point to its nearest centroid. Step 2, we will reposition the centroids. Step 3, we will assign. Step 2, assign, reposition. So you keep repeating step 2, step 3. See how the centroids are changing. So keep repeating step 2, 3, 2, 3 until there is no further change that happens. So the end result of clustering, that is what is more important. Now, this was all the theory that I took you through. But the end result of clustering would be, I give you any data, and the clustering algorithm or the clustering model will give me the centroids of my data. Okay, it will clearly tell me that, okay, there are these many number of groups I can see, and these are the middle point of your groups. The middle point of the groups will somehow tell me the average behavior of that group, isn't it? I mean, if you relate it to the the beautiful customer segmentation use case that we discussed, so if I can tell you, the centroid of the group, if I can tell you that there is a group and the centroid, the middle value is this, inherently it means what is the average behavior of the group. It tells you on an average how the group behaves. Okay, so if you relate it back to the initial conversation we were having, customers spending time, customers spending money. So when you have a centroid, the centroid will kind of tell you the average time spent, and it will tell you the average money spent. What is the average time the customer spent, and what is the average money the customer spent on the site? Okay, so this is going to somehow define the group for you. Okay, so we've got one more very interesting analogy that I wanted to take for everyone. This is another very nice animation that I wanted to play for all of you. So you can see. Let me kind of play the animation again. I'm not showing the algorithm again because all of you recall it to some extent now. Look at this one. So first step, you can again see that we are going through the centroids. Okay, everyone can see this now. You can see first step we are initialize. Second step, assign every single data point to its nearest centroid, and third step, reposition. See, this is assign, then reposition. Again assign, then reposition. So it goes through the step 2 and step 3 are repeated multiple times. We repeat step 2, step 3, step 2, step 3 multiple times until we are able to find the exact values of the centroids. Okay, so this is again the theoretical part of the algorithm that we discussed all this while, just to tell you how the algorithm is working per se, right? I can play this once again for you. This was a little bit fast to take in. So let's look at another analogy. So here it goes. And once again, you can see step one, we initialize the centroids, the four centroids. Step two is assign. So this is step two happening. We are assigning every single data point to its nearest centroid. And then step three, reposition. The centroids are repositioned. See, the greens are repositioned. Again, step two, assign. Step three, reposition. Step two, assign. Step three, reposition. So we keep repeating steps two and three, steps two and three like this until no further, like until we get the exact positions of the centroids. So that's the way how the k-means algorithm will play out. So now we'll go to a real use case. We'll go to a small case study in terms of how to implement k-means, because that's again the major focus for us. We're trying to see implementations, how it is implemented. So let us go and check how the k-means clustering algorithm is implemented. And before that, there's one more small related concept I would like to discuss, which is how to decide the number of clusters. Okay, because if you look at the last case study, the last example that we did, I initialized the number of clusters to be 3. So I straight away said n clusters equal to 3. So you find out the 3 clusters for me. But it is also very important because clustering is an unsupervised learning problem. There has to be some way for us to know how many groups we want to form, right? And that is exactly what we will briefly see, how we can use different methods to find out how many groups or clusters to even form. Because the k-means algorithm, it needs the argument. You have to tell it in advance how many clusters you are looking to create. So how to know how many clusters we should go for? Should I go for 3 clusters, 4 clusters, 5 clusters? How do we do that? Okay, so this is just one of the approaches that we can use. There are many other approaches that are there. So what we are doing here conceptually is we are calculating something called inertia. So we are using the inertia metric to calculate the error that is inherently present in the cluster. So we are measuring the error in the cluster using something called inertia. Okay, I repeat again, we are measuring the error in the cluster using something called inertia. And what is inertia? Inertia stands for SSE. SSE is nothing but sum of square errors. So first we calculate the error, then we square the error, and then we calculate the sum of the square errors. This is the 3-part process we are following. So first we calculate the error. So we are trying to calculate some kind of an error. Error in this case is nothing but distance, right? So if you have a clustering model, how do we inherently think of the error in the model? The error is nothing but the distance, basically. How far is the data point from the centroid? That is how we define the error. Okay, so when you do clustering, let's say this is the distribution of data points I have right now, and you find out the centroid. Let's say I did k equal to 4 as an example, right? This is just to explain to you how clustering is happening. Let's say you end up doing k equal to 4. So when you do k equal to 4, when you do clusters equal to 4, what is going on behind the scenes? So when you do clusters equal to 4, when you do k equal to 4, behind the scenes, you are able to find out the centroids, right? Now that you did the clustering, you want to find out you want to now find out what is the inertia of the model. What is the overall inertia of the clustering model? That is what you want to find out. So first you calculate the error, then you square the error, and then you find out the sum of the square errors. So error is nothing but the distance of the point from the centroids. That is how we calculate the error. So we take each and every data point and we find out the distance from the centroids. So we find out how far are these points from the centroids. That is the error. Then we square the errors, and then we find out the sum of the square errors, SSE. Mathematically, if I have to formulate the mathematical formula, it's quite straightforward. You can see that each of these distances of the points from the centroids, these are the distances, like D1. D1, D2, D3, D4, D5, D6, D7. So these are the distances. So first we take the distances D1, square it up, then sum it up. D1 square plus D2 square plus D3 square plus Dn square. So it's actually summation Di square. That is how we define the inertia. Why are we talking about it, right? Why are we talking about inertia? Let's see that. So now what we can do is we can actually plot a graph. We can plot a graph here and say that, hey, whenever the number of clusters is one, see here we have done 4 clusters, right? Because 4 clusters is kind of optimum. It's very obvious, right? I mean, if you look at this diagram visually, everybody can make out that 4 clusters is kind of optimum here. It is optimum here. So that's what we are doing here. We're trying to create 4 clusters. But what if I create one cluster? What will happen if I try to create a single cluster out of the whole data? What will happen if I try to create one single cluster? So if I try to have a single cluster for all these data points, the inertia will turn out to be very high. The inertia value that you end up getting will turn out to be very high. You know why? You know why the inertia will turn out to be very high? Because the distance of the individual data points, like, if I just annotate it and show you, okay, imagine I have a single cluster. So all these points are part of a same cluster. If I do that, then all these data points will be very, very far away from that centroid, right? If I have a single centroid now, so the inertia will be very high. So for cluster one, inertia will be very high. That is one extreme. The other extreme would be if I have too many clusters, or in other words, if I have too many centroids. Let's say in my diagram right now, I have 100 data points, right? I have 100 individual data points. Every point is a customer. So if I try to identify 100 centroids, if I try to identify 100 centroids, what will happen? The inertia will become zero, friends. Because every data point is a centroid now. And it's like you have got 100 points and you've got 100 centroids. So what is the distance between every point and its centroid? It's zero, right? Because the point itself is a centroid. That is the other extreme. So inertia equal to clusters equal to 1, inertia will typically start very high. And clusters equal to 100, like as many as data points we have. So inertia will tend to 0. We are trying to find out something in between. So as the number of clusters increases, you start with clusters 1, inertia is very high. And as you go from clusters 1 to clusters equal to 2, clusters equal to 3, clusters equal to 4, as you increase the number of clusters, right? So as you increase the number of clusters from 1 to 2 to 3 to 4 to 5, as the number of clusters increases, what will happen? The inertia will continue to decrease. So you can see very clearly we go from 1 cluster to 2 cluster, inertia has dropped a lot. You go from 2 to 3 clusters, inertia has dropped a lot. 3 to 4 clusters, inertia has dropped a lot. Now this is kind of the optimum part, right? 4 clusters kind of seems like optimum. So from 1 to 4, you're seeing a very big drop in inertia because the quality of the model really improved until 4. Now 4 to 5 onwards, something very interesting will happen. The inertia will continue dropping. Definitely, see, mathematically, the inertia will continue dropping because the distance will reduce, right? But we seem to have achieved some kind of an elbow here. This is a bend. And this is what we call the elbow method. This is the elbow method that we are calling. Why is it called elbow method? Because we are trying to find what is the point where we achieve that bend. So from 1 cluster to 4 clusters, it has dropped a lot. 4 to 5, 5 to 6, 6 to 7 is kind of stagnant. It won't be exactly stagnant. It will still reduce, but the rate of reduction is low. So that is that bend that you are trying to find. And this is the way we can, this is one of the most rudimentary ways we can use to determine the optimum number of clusters that we have in clustering. So given any segment, clustering problem, you can straight away do an elbow method because you don't know, right? Say real world data, we cannot visualize. Here we can draw a scatter plot. That's why it's so easy. You can look at this and say, hey, I can see there are 4 clusters, but hey, what if I give you 10 dimensions? This is a two-dimensional data. It's a 2D data. That's why you can see a scatter plot and you can visually see. But in reality, you will not have a 2D data, right? What if I give you, like the diabetes data from yesterday, and I ask you, please tell me how many groups or clusters of patients we have? How will you do that? How will you study all the 8 different features and tell me how many groups are there? So you need an algorithm. You cannot do it, by hand. You cannot do it visually because you cannot visualize. How do you visualize 8 dimensions? You cannot, right? So so that is exactly where these kinds of approaches are very useful. So you take the whole data, you plug it into an elbow method. You try to find out, okay, clusters one, what is the inertia? Clusters two, what is the inertia? You try to find out that bend, that elbow. And that is what tells you the optimum number of clusters. And once you have the optimum number of clusters, then you can use the k-means algorithm. You can say k-means, and you can find out the exact value of the centroids. And that is exactly the process that we will use now. So we'll go to our very first hands-on example where we will use this exact same process. Okay, so we'll do a small hands-on exercise, and based on that, I will give you a hands-on exercise. And over the course of the next half an hour to 40 minutes, we should have a very strong understanding of how to do clustering. Because I see clustering is going to be a big part of the work that you do. Okay, you're also looking at a lot of machine data, a lot of log data, like a lot of network parameters data. So this is actually a very good use case for a lot of you, right? Because you might want to look at your network parameters data and find groups, find clusters, because there are no labels, right? You're just looking at data that is getting accumulated every timestamp, every millisecond, every second level data you're getting. So it's going to be a very good use case where you want to find groups, find clusters, find anomalies. Okay, so this is something that you can relate to. So this is my data set. The example number one that we are taking up, we are looking at a very simple data set. We are taking a two-dimensional data, you can see. When I do data.head, I am able to see V1, V2. V1, V2 are the two features we have right now. And we can also see the values of the features. Now, V1, V2 are completely hypothetical features we have taken. They could mean anything. You can put you can put a face to the names of the features. You can say V1 is, let's say, time. V2 is, let's say, money. You can think of it in the Amazon context. So V1 tells you how much time the customer is spending on the website, and V2 is telling you how much money the customer is spending on the website. So both of these parameters you're tracking. And now what we will do? Now what we will do here is we will go and on the basis of this data, we will go and try to find out a couple of things. We'll try to figure out how many groups and clusters we have, and second, we'll try to figure out what are the centroids of the clusters. Okay, so let's do it step by step. So first, we will use the elbow method. See, I'm not taking you through the code because this is just Python. I think people are fairly comfortable with coding here, but it's straightforward. What we have done is we have actually used a range function 1 to 20, and we are iterating through this in a for each loop, and we are basically building different k-means models, and we are basically computing the inertia underscore. So it is a straightforward method that libraries that we are using, and at the end of it all, we will get this. We will see, okay, n clusters 1. When we have one cluster, in error is this much. E6 means 10 power 6. When clusters is 2, see the error has dropped 2.3. When clusters is 3, 6.11. And this is how we can visualize it. See this beautiful elbow that is getting formed. Can you see, all of you? You can see that when the clusters is equal to 1, the inertia is very high. When the clusters goes from 1 to 2, the inertia has dropped. And when the clusters goes from 2 to 3, inertia has dropped further. So it clearly tells you that as the number of clusters have increased from 1 to 2 to 3, as we have increased the number of clusters, what has happened is the inertia has continued to drop. It has gone from a very high value to a very low value when we have 3 clusters. Now 3 clusters to 4 to 5 to 6 to 7 to 8, it is kind of stagnant. It is still reducing, as I told you, it will still reduce, but the rate of reduction is not as high as what we had here. So this is the elbow. So very clearly for this question, what is the optimal number of clusters? What is the optimum number of clusters? The optimum number of clusters we have is equal to 3. So first step, you find out what is the optimum number of clusters. And once you have the optimum number of clusters, then you go and use the k-means algorithm. We have a straightforward library that we can use. This is k-means n clusters equal to 3. and we do k-means.fit of x. Remember, in unsupervised learning, clustering, we don't have any output y. So even from a code perspective, when we use the sklearn algorithm, we don't say x comma y. Okay, we will simply say k-means.fit of x because you're simply using the features and you're trying to build the clustering model only on the basis of your features. So we will say k-means.fit of x. So we will build the clustering model, and then based on whatever model we have built, we will do the prediction and we will find the cluster centers. This is the end result of what we will get. Okay, see, so we have the original data points and we have created a new column called group. And what is this group? The group is nothing but k-means.predict. So whatever k-means.fit I did, I do k-means.predict to get the labels, and these are the labels that I'm visualizing. So this is the workflow. The original data was this, right? V1, V2. This is the original data. The first step, you figured out how many groups we have. That was the inertia elbow method that we used. So, and then we use k-means to find out the exact positions of my centroids. And based on that, we are able to say that, hey, you know what? Data like this is part of group 1, data like this is part of group 2, and data like this is part of group 3. So now we are able to say what each and every group of data entails. Okay, so that's the thing we are able to make out here overall. And we can visualize it in this way. You can see this is the way how we can think of clustering. And as I told you, like here, I know it looks very easy here because it's just 2D data, but it becomes more challenging when you have multi-dimensional data. In that case, you cannot visualize it in this manner. So if you have to visualize it in that sense, you need to create a pair plot. Okay, so especially for a two-dimensional, multi-dimensional data, if you want to visualize, then you will have to create a pair plot like this to visualize. Okay, you'll have the diagonals. So if there's V1, V2, V3, V4. So look at the diagonals, and then you can visualize the data in this pair plot. Okay, and we'll see some of those use cases as we go along.